Why shall we get started?
I think so.
All right. So welcome everyone to the IQM Quantum School. So my name is Danny Bulmash. We'll be introducing ourselves briefly in a moment. Um, but we're very excited to have you all here today. And we're excited to talk about quantum computing and get you going on this very exciting technology that we're all very passionate about. So I just wanted to start out by giving you a sense of what to expect. So the first day is going to be on the foundations of quantum computing. So we're going to assume no quantum knowledge whatsoever, and really start for quantum newbies and get you building your first quantum circuits by the end of the day. Day two, we'll be talking about algorithms. So we're going to implement a couple of quantum algorithms and run them on the quantum computer. And on day three, we're going to start talking more about hardware, about how things get turned from the circuits that you program into physical pulses that interact with the machine. Um, so we will be providing the recording afterwards, and there will be a certificate available. We'll go into a little bit more of the logistics in just a moment, but before that, your instructors would like to take a few moments to introduce themselves. So Stefan will be giving the lecture today, so perhaps he can go first.
Awesome. Yeah, I'm Stefan Segerer. I'm the head of product quantum platform at IQM. I'm originally from Germany and speaking to you now also from Germany, part of IQM's German branch, and have a background in computer science. And I always love teaching and explaining things. And that's why I'm so excited to be able to share with you what quantum computing is about, why we think it's exciting, and how you can also get a sense of what it can do for you, for society, and how you can participate in quantum knowledge creation. Over to you, Danny.
Yeah, so my name is Danny Bulmash. I'm the education lead here at IQM, based in the Munich office. Though, if you can tell from my accent, I'm American. Um, my background is in condensed matter physics. My training is as a theoretical physicist in all things quantum. So I'm very passionate about teaching and engaging with a wide audience and talking to people about quantum technology and quantum science. So I'm really excited to get into the meat of things and get you all working on quantum algorithms tomorrow. Over to you, Nadia.
Yes, thank you. So, good morning, everyone. I'm Nadia. I work in IQM as a quantum education specialist with Stefan and Danny. And I think what really motivates me is like days like this one. It's super nice to like see that you are all very excited to learn about quantum computing. My background is in physics. I have a PhD in quantum information. And yes, I was like, from the moment I learned my very first lecture of quantum mechanics, I knew that this was going to be like my life. So I hope today we can spark also this enthusiasm in you. So, yes, thank you so much for being here.
So I think all of us had a similar experience in that first quantum lecture. So a little bit of logistics for today. We're all very excited to work with you. So what to expect? So each day is going to have about 1.5 hours of live lecture with some pauses for some interactive activities. We'll post the links on screen and in the Zoom chat. If you have questions during the lecture, the easiest way to get them answered is going to be through the Q&A feature. It will be difficult for us to monitor chat, but if you submit questions through Q&A, we will be monitoring that carefully, and we will either be answering them in Q&A on Zoom or live during the lecture. We'll then have a short break, and then we'll move to lab and Q&A. So there will be some notebooks that you'll be able to experiment with that will guide you through coding quantum circuits and running them on IQM's quantum computers. We'll demonstrate some of the notebooks, and then we'll be here for Q&A time. So each notebook does have some homework, which you're encouraged to complete on your own, and we will post solutions to this. And these notebooks will guide you through running programs on our quantum computers. So it should be an exciting time to get to run on actual hardware. So in terms of prerequisites, we will be doing some coding in Qrisp, which is a framework within Python. But we're not going to assume a lot of coding background. If you've worked with lists and functions and those sorts of things before, you should have enough coding background. The only math background we're assuming is high school level algebra, but it's helpful if you've worked with matrices before. And then finally, for some technical requirements, you should have received an email from us about your account on IQM Resonance. When we start the lab, I think Stefan will be talking a little bit about getting that going for you. But you do want to make sure that your Resonance account is working so that you can run programs on the quantum computers. And you will need access to Google Colab, which can be done through any Google account. So if you don't have either of those set up, you can do that during the break after the lecture. So I think that's all we have for the logistical parts of things. And indeed, there will be recordings, slides, and notebooks all posted afterwards, so you'll have access afterwards. And Stefan will talk a little bit about certificates for the course. But with that, let me turn things over to Stefan to talk about day one and get started with the material.
Awesome. I'm really excited to get now started with the content. Before we dive in, let me give you again an overview of what to expect today. Our goal for today was to enable quantum newbies to join our quantum school as well and go out with a solid foundation for understanding quantum computing, not just for the days to follow, but also that you'll be able to gain your first hands-on experience with an actual quantum computer. So we'll look at what kind of problems can a quantum computer tackle or approach. We'll explore how quantum computers are different from classical computers. And we really try to keep things intuitive and focus on the concepts that really matter for practical use and not so much the heavy math. So we kind of try to focus on the underlying ideas and make those tangible and visible to you. And finally, we'll use Qrisp to run our very first quantum computations on some real hardware. And I think by the end of the day, you'll not only understand the basics, what's the concept behind quantum computing, but you'll also have executed your first quantum algorithm, quantum circuit. And before we dive into, I want to explain to you who we are as a company. We introduced you as persons, but we also represent IQM. And with IQM, our mission is, or the mission that drives our work is, we want to build world-leading quantum computers for the well-being of humankind, now and for the future. That's the mission we kind of support or work towards. Because there are things where quantum technologies, quantum computers can really have an impact, make a difference. So this mission guides us in every decision we make, from kind of the technologies we develop to the partnerships we pursue, also to things like this quantum school that we organize. And quantum computing is about pushing the boundaries of science, yes, but it's also about enabling real solutions to some of society's most important challenges. And this is what we are driving here today. In numbers, we're around 300, a little bit over 300 people that work towards making this mission a reality. We're glad to have been backed by some very great investors that allow us to pursue this mission. We've also built more than 30 of these quantum computers, and some of these you'll be able to work with throughout this school. What I think makes it an exciting place to work is that we've over 50 nationalities within IQM that help us make this a reality. Currently, we're working on getting our 150 qubit chip out, and more than 10,000 people use our cloud platform, IQM Resonance, and you'll be part of these people that use it as well. And we are globally present, so these are just some locations where IQM is now present, but we've also delivered or are delivering a bunch of systems across the world as well. And so I don't know, in Europe, our systems are running places like LRZ or Jülich or VTT in Finland, Evident in France, Sinica Links in Italy, in Poland, in the Czech Republic. There is a system in South Korea or in Taiwan. And quantum school kind of really fits to our understanding of how to advance quantum computing. We believe that in order to make quantum computing a successful tool for society, we need to share it with as many people as possible. And that's why we do something like this. Yes, it's about you understanding what quantum computing is about, get a feeling if quantum is something for you, be inspired and curious to learn and explore more. But we also believe that there is a need for more talent in quantum in order to tackle those problems we have as society. And to motivate you a little further, and kind of because these questions were asked, we do provide certificates. This is roughly how this will look like. So it's digitally verifiable. So you'll get that if you attend. So how do we track attendance? We can't check this automatically from here. That's why in every session we hide, not really hidden, but at least we include a QR code that you, or link, that you please open and visit and enter your email address there. It's important that you use the same email address you signed up for Quantum School. That's what we automatically compare against. And if you attended 2 out of 3 sessions and also worked using Resonance on 2 out of 3 problem sets, then we are handing out the certificate automatically to you. So the first QR code is actually not hidden. I thought I'll just provide it directly here to you. So Danny or Nadia will also post it to the chat. And you can also scan the QR code, quickly enter your email address. There should be just one step. We'll delete everything afterwards. This is really just so we can make sure we hand you out their certificate as you attended enough sessions. Could someone, Danny or Nadia, could you also share the link to the chat? That would be great.
Working on it.
Okay, perfect. You can also obviously do this on the side. The first question, so kind of, I want to now give us the big picture. Why do we do what we do? Why do we build quantum computers? Why do we actually think that we need a different computing paradigm? I mean, computers are pretty powerful. The one I have here, my smartphone, they are all pretty powerful. And so are all those supercomputers we have around the world, right? What we've now seen with AI being possible, I think, is great. It's insanely great. So why is there still a need for some different approach to computing? And in order to answer that question, the QR code is not working. Oh, sorry, if that's the case,
we'll get the
link to the chat.
We'll get the link in chat in just a moment.
So we'll post the link to the chat, then it's anyway easier. So in order to show you why we need different computing paradigms, I want to select an example that kind of makes this more obvious for us. And I'll use an analogy. I have a pack of spaghetti here, and Nadia, I'm sorry, it's actually not spaghetti, it's bucatini. I don't know which region they are from, but they're a little thicker, so you see them better. And I want to explain how different computing paradigms can have an impact on what we can meaningfully compute by using the spaghetti computer. And the best way to approach this is by thinking on how to solve the same problem with 2 different approaches. And I think maybe it's because I've taught too many introductory computing courses over the years. But I think the best problem to possibly select are sorting algorithms. Not because sorting is particularly important to solve. No, but I think because it's very good to kind of give an understanding of complexity. And so today we start with a simple sorting task. Think of a list of numbers that needs to be arranged from the largest to the smallest. And I have 4 numbers here that I'll now use, 8, 2, 5, and 3. Let's first think about how we can solve this on a regular computer. Okay, one thing is obviously we can go through the list and always store what is the biggest one, like the biggest number or the smallest number, both is possible. So in this case, it's the smallest number. After we went through the list once, we can move the smallest number to the beginning of the list and know, okay, this part in the front is now sorted. Let's continue with the rest of the list, consisting of 3 numbers, 8, 5, 3. We can repeat the same process, right? So I again look for the smallest number and voila, we have a sorted list to some extent. Still 2 numbers are not yet sorted maybe, so let's check them. And after going through them, we've actually figured, okay, they're already sorted. So what's important here is that we've counted the steps here in the top right corner. And essentially for every element in the list, we've roughly needed to check the list once. Obviously, the list got a little smaller on the way, but on average, we've roughly for every element went through the list once. And people who have sit in too many computer science lectures will tell me, okay, yeah, there are better ways of doing the sorting. There is something that can do it a little bit better, like quicksort or something. But let's ignore this. There are some slightly better algorithms, but we can't get it anything like magnitudes better. So let's think about a new computing paradigm that can lead to more efficient solutions, maybe. And this is where my spaghettis come in, right? And so with that, I need a pack of spaghettis, or bucatini in that case. And how can I approach that task now? Let's get my 4 numbers again. And I'll just take 4 spaghettis now, 4 straws of spaghettis, right? And obviously they don't really represent numbers. They are just equally long. So what I could do is I could encode my numbers into the length of these spaghetti. That's the 8. That's my 2. That's my 5. So this should be roughly half. Don't need that one. That's my 3. Voila. So there we go. 4 spaghettis, right? Not really sorted, but I've now done 4 operations. What can I do with those? Okay, it's spaghettis. So I could cook them, I could serve them with bolognese or whatever. But what I can also do is the thing I do before I put them to boiling water is I place them on the palm of my hand to align them evenly. And voila, I actually have a sorted list already. I can go ahead and now take the biggest straw, place it on the right-hand side of me, take the next biggest straw because I can like go from top to bottom, select the 3rd one, and then I have the 4th one left and also place that on the screen. And the complexity, if we count the number of operations we've needed, is we've roughly needed to go through the list of numbers twice. Once to encode the length, and once to read them out or place them on the table once I've sorted it with 1 step. And this is also what this animation tells us. And instead of roughly squared n operations that I need, I've used 2n plus 1 operations to do this sorting with spaghettis. So by changing the means of computation, I was able to reduce the complexity it takes to sort this list of numbers. Obviously, you could say, well, but touching spaghettis takes way longer than looking at a number. And that's correct. That's actually also true for quantum computers. So you need to get to a point where it's okay that even though every operation takes a little longer, the overall time it takes to complete or solve the problem is still smaller because you need so much less steps to solve the problem. And the fact that information is physical is not something new. Obviously, the spaghetti computer, even though it's kind of physical, but it's more like cute. But does it really scale beyond noodles or beyond pasta? And the answer is yes. When Rolf Landauer said that information is physical, what he meant is that computation just doesn't happen in abstract logic. It obviously happens in the real world, inside a physical system that obeys physical laws. And sometimes those systems can perform very specific computations, incredibly efficient. For example, here, we are looking at the complete elliptic integral of the first kind of this very specific problem. I guess if you would solve it on a traditional classical computer, you'd potentially do some numerical processes and stuff. But a pendulum, a physical pendulum like this thing here that you maybe know from high school physics, is also solving this integral. And a pendulum actually computes the quantity here naturally. Its oscillation period directly codes the value we are looking for. Obviously, it might take a few minutes to set up the pendulum. But obviously, that's still much faster than building a classical computer from scratch. That's one thing. And also then, the task to solve this integral, the pendulum, is very, very effective in it. And again, I think we see different physical paradigms, different strength. And we want to transfer this to the quantum realm and enable us to use a different computational means for information processing. The means of small systems that obey the law of quantum mechanics. And we do that because even though computers are very, very powerful, classical computers, there are still some problems that these computers cannot efficiently solve. Some are maybe mathematical limits, because some problems, they just explode in complexity so much. And some of these things, like factoring integers or large numbers, or simulate, are like at the ground of why we have safe encryption on the internet, while others are just cumbersome that we can't solve them because we can't fully understand maybe how some chemical reaction is happening. Then there are physical limits. Transistors can't shrink forever. We're approaching atomic scales. On top of that, we have some time or power limits. Like at some point, it's just not worth the wait to get a result for a computational problem we want to have solved. And some studies even estimate that a large chunk of what we use for energy and stuff is going towards global computing. So obviously, if we can create other solutions there, that's great. And these problems that a classical computer cannot efficiently solve, they're typically displayed with a graph like this, where we have the problem size on the x-axis and time to solve the problem on the y-axis. And typically, small problem sizes are rarely a problem for any computer whatsoever, like any classical computer. But the more the problem size grows, the more likely it is that it doesn't scale like linearly. Adding an additional element to the problem size just increases our runtime by 2 minutes, but kind of maybe doubles or triples our runtime. And then very, very fast, you'll get to a point where it really makes sense to think about other problems, other solution types to approach this problem. And that's what we do with quantum computing. We think about which problems can we tackle or address where a classical computer at some point will just hit a roadblock. And the thing we have here is that even though a quantum computer is similar to the spaghetti computer, not technically faster, it operates in like megahertz range. And a classical computer, like even my smartphone, I think has like 1 or 2 gigahertz per kernel or per core. Even though it operates in megahertz range and is therefore, like on paper, slower, it can still solve some problems faster or better because it can use different means of computations and therefore also different strategies to solve the problem. So different algorithms. And those problems are in a bunch of different application areas. You can roughly divide them in quantum simulation, quantum optimization, artificial intelligence, machine learning. And there are some other problems like the factorization problem that are harder to sort into or to sort into category. Quantum simulation is understanding how acid something is, how likely it reacts with something. Problems like how to more efficiently produce fertilizer, which is a very energy intensive process, how to build better batteries. Optimization is like optimizing financial portfolios, product portfolios, and other things. Machine learning, I think I don't need to give examples what we do all in machine learning. I've brought with me 3 examples of projects we are working on with partners. One of the most exciting areas where quantum computing can make an impact is in sustainability and preparing or creating better materials for specific problems, such as batteries for electric cars. This is something we've done in work together with the Volkswagen Group, where we've looked into how quantum computers could support creating batteries with a higher lifetime, batteries with faster charge-discharge cycles, and so on. Other questions could, of course, include higher energy densities, materials that are easier to source, maybe more environmentally friendly, and these kind of things. So to understand why quantum computers are useful in something like battery research, we need to zoom in a little bit on some specific area of the battery, specifically the electrolyte region of the battery. And this is where a lot of the key chemistry happens. Ions move, reactions take place, and so on and so forth. And the overall performance and lifetime of the battery is determined here. And the challenge is that this region contains electrons that are strongly correlated. In other words, their behavior is deeply interconnected. What one electron does depends heavily on what the others do. Kind of in quantum terms, they become entangled, and this is what we can use, or why we can more efficiently simulate it with a quantum computer than we can do with a classical computer. With quantum phenomena, and we simulate our quantum particles, and we simulate them with other quantum things. Another example is from a different area, and this was done with a global insurance company where it was about fraud detection. So the challenge was to detect unusual and suspicious activity across many data points. And it's about spotting that one strange pattern that is hiding in a sea of normal, regular behavior. Like tapping your credit card creates a data point. And obviously, you create a lot of data points throughout the day. But maybe there is some activity that happens at a very unusual time for you because you normally sleep there. Maybe it's okay because you're traveling and you don't want your credit card to be blocked while you're traveling and you're just getting your rental car, and your card is blocked because of suspicious behavior. I mean, this can happen, but this is obviously not what you want. So you really only want really fraudulent behavior and not these kind of behavior. And also here, quantum algorithms were explored to check how can they support these kind of problems. Another problem is more from the optimization side. The one here was from machine learning. Now we have optimization. It was done together with a French electricity provider, EDF, and the challenge was to plan maintenance for a whole fleet of power plants without ever risking a blackout. And the objective kind of sounds simple. Create a maintenance schedule so that every plant is serviced regularly, but never take too many of these plants offline at the same time. So in practice, there are a lot of constraints. Maintenance must happen at fixed intervals. Like there are regulations, I don't know, do maintenance once a year or these kind of things, similar to our cars. But you also have to kind of do some service every 1 or 2 years. And teams and equipment to do those maintenance are limited, so you can't do them all at the same time maybe. And the grid also has to be meeting the demand every single hour, because restarting an energy grid is something that's very, very difficult. I think we've seen that in Spain this year. And when we model this as a graph problem, and that's what we've been doing, each possible maintenance window is a node, and the edges mark the combinations which are incompatible. And this is an optimization problem that can also be tackled by a quantum computer. So before we can obviously understand how the quantum computer can solve those problems, we need to look into what a quantum computer actually is and how he operates. And we've only seen so far that some problems scale very fast for ordinary digital computers, meaning that computers need a lot of time, maybe also memory, to solve them. Something for some problems we just cannot afford or can't even create or build. Then, different physical systems may offer different computational complexity for problem solving. And quantum information processing can reduce computational complexity for some tasks. And really, this sum can't be highlighted enough. Not every problem is better solved on a quantum computer. Only some problems are better solved on a quantum computer. And when speaking of quantum computers, a bunch of pictures come to our mind. So here I've selected 3 images. The first 2 are IQM systems. The third one is an ion trap machine. But similarly to how classical computers can come in various forms, shapes, or sizes, quantum computers can also come in various forms or sizes. And the means of computation can actually be different quantum elements. It could be that we use atoms, it could be that we use ions, it could be that we use electrons, it could be that we use photons. So all these allow us or exhibit quantum phenomena, quantum attributes under specific conditions. And what we do is we build based on superconducting technology. That's a way of, let's say, building artificial atoms to a way, but that's something we'll only dive into more on day 3. What we want to look into first is not why quantum computers look like from a sci-fi movie. Unfortunately, there you need to join day 3 again. But we want to look at the logic behind it. So what they actually do, because they not only replace the look and feel, what they also replace is the logic unit that we use. And that's where it comes to bits and quantum bits, qubits. So they don't only look different from the outside, but they also look different from the inside. And that's why I want to start with the basic unit of information. Classical computers operate using bits. Okay, quantum computers use qubits. Okay, what's the point? It's called differently. Maybe let's start first with reminding us again what it means operating with bits. So a bit could technically be any everyday physical object that can be clearly in one of 2 states, like a switch that is either on or off. And we typically in computing or in computer science, we label those states as 0 and 1. Everything your laptop or phone does is built from manipulating billions of these tiny on-off switches. Okay, obviously in our computer it's not physical hardware switches, but it's more like that we have electricity or voltage low and voltage high as like 0 and 1. And what's important is that when we measure a classical bit, kind of retrieve its information, check if it's a 0 or 1, nothing strange happens. Okay, why is he even telling me that? That it's just giving me the value that I measure, voltage low or voltage high. It's because in quantum it will be different, and you'll see in a bit. But everything we compute and process on a computer is done using those bits. It's done by manipulating those zeros and ones. And there is a logic or a rule on how those zeros and ones translate to the things we actually care about. Photos, videos, music, text. And in this example, we've stored the message IQM in bits. So every letter can be represented by a specific length of bits. This has to do with the encoding that is used and a bunch of other conditions, but there are some basic encodings that typically everyone uses. And because those conventions exist, we can not only create and store these kind of information, but we can also share them, process them, and so on and so forth. Because Photoshop knows how to process image data, an LLM knows how to process text data, and so on and so forth. A quantum bit is a little bit more. It's a physical object that can be in a superposition of two states as well. So it plays by a very different rulebook. It's not just limited to 0 and 1 or 1. Instead, it can be in a superposition, which means it's kind of a combination of 0 and 1. And what type of combination we'll explore together. We often represent this using the surface of a sphere, called the Bloch sphere. And every point on the surface of this sphere is a potential state our qubit can be in. And now comes the catch, why I said something about measuring classical bits before. It's the moment that we measure a qubit, figuring out where on Earth is it, or where on this Bloch sphere is it, it irreversibly snaps to either 0 or 1. And this behavior is one of the key differences of quantum computing. And obviously, it's not that like one qubit is very exciting, because a single qubit can only be in one of two states or in a superposition of those two states. That's not very exciting. You can't do a lot, right? But if I add a second qubit, I already double its basis states that it can form a superposition out of. A classical bit could obviously only store one of those 4 possible states at a time. Obviously, it can represent all of them, but only one at a time, whereas qubits can exist in a superposition of all of those 4 states. This means that instead of holding a single configuration, the system can hold a combination of it. And if I continue that with 3 qubits, I get into a superposition of 8 basis states. With 50, I already get to like a roadblock for classical computers. I think that's like 2 to the power 50 is already more than a quadrillion for sure. And a classical computer would need to keep track of all these different factors of all these basis states. And this becomes very quickly impossible. And that's why simulating 50 or more qubits on like classical computer would really already require so much memory that only maybe, if we connect really the biggest supercomputers that we have, might roughly get to it. And then one operation would even take forever. And okay, you could say, well, I have the spare money around and in my pocket, and I can buy a classical supercomputer for, I don't know, $400 million. Nice. But what do you do if you need to solve a problem that doesn't require 50 qubits, but I don't know, 51 qubits? Do you still have the pocket money to acquire 2 of these computers? Because that's what you would need to double the computational space complexity needed here. And we can take this to the extreme and go to 300 qubits, because that would, in theory, get us to a point where the number of possible states is 2 to the power of 300, which is a number that even exceeds the number of atoms in the observable universe. Of course, having 300 qubits doesn't mean automatically we can solve all problems instantly, but it would mean that quantum computers operate in a computational space far beyond what classical systems could like even hope to represent. And the takeaway here is that quantum computing provides an exponential increase in the computational capacity. And obviously we need to use that clever, and how we use that clever is something that we'll speak about for a long time for sure. But this is also why researchers, governments, companies around the world are checking or investing in quantum technologies, because the potential for scientific and industrial discovery here is enormous. And we're obviously just at the beginning of this process. And now that we know, okay, they are powerful, they increase the computational capacity I can work with, but how do I actually work with it? That's really the next question. How do we control a qubit? How do we change its state? And how do we build computation that make use of these quantum effects? And there are different ways to work with qubits. I'd say typically there are like two main types, two major approaches that we might separate between. I mean, there's more stuff that we could discuss, but there is quantum annealing that you might have heard of, which is specific devices that are not really universal quantum computers, but that are purpose-built to solve specific optimization problems. Typically those that can be phrased as find the lowest energy configuration of something or minimize this given problem that is given in a specific form. So potential problems, route optimization, scheduling, portfolio, these kind of things. What we want to look into during this school is what's called gate-based quantum computing, which is what you could say is designed for universal quantum computing. Gate-based systems apply so-called quantum gates, specific operations, similar to the operations that my spaghetti allowed. They are different, obviously, to classical operations. And they are much more versatile in running algorithms such as the one that is finding prime factors, that is solving chemistry simulations, some machine learning problems as well. But more on that in a moment. In order to explore how a quantum operation or quantum gate operates, I want to take a step back again and start from where we are at, what we know, at least roughly, how a classical conventional computer operates with bits. Because, well, we had bits are the foundational unit of information they have. And everything a classical computer does, whether it's turning on a light, running some graphics rendering, running a video game, processing data, generating LLM output, is ultimately built on those bits and on manipulating those bits. And typically, we can imagine this as a input, compute, output process. And I visualized this here as well. This is the input, the line is the processing, and the light bulb is the output. Obviously, by changing the input, I can have an effect on the output. So I turned the switch on and the light turned on as well. Now, the processing that was happening here is essentially nothing. It's just a cable or a line here. But I could put some logic gates here. Logic gates are tiny electronic components that take bits or electric signals as inputs, apply a rule, and output a new bit. We'll only look at the logic implications those gates have, not like how they are implemented physically. But for example, I could add in here a NOT operation, right? And even though the light switch is still on, the light bulb is now off. And the role of this NOT gate is very simple. If the input is 0, the output becomes 1. If the input is 1, the output becomes 0, right? So it inverts the signal. And by combining millions or billions of these tiny gates, classical computers can perform all the computation we rely on today. Obviously, with one bit, that's not very funny and not very useful. That's why multiple gates form a circuit. So kind of this overall thing we can call a circuit. And an algorithm is implemented in a sequence of gates. Circuits are represented as a time sequence, similar to like musical notes. And it doesn't matter what type of technical diagram that now is, there are two operations. One operates on 1 bit and the other operates on 2 bits. And actually, that's just a side note. We have 2-bit signals coming in and 1-bit signal coming out. That's something you'll never see with quantum circuit diagrams later, because classical circuits are irreversible. In this case, if this is an OR gate, for example, like a gate that counts, is there at least one signal coming in? If the output is 1, we don't know. Was the input 1, 1? Was it 1, 0? Was it 0, 1? All of these are possible. And you'll see later why this makes a difference. And now I've spoken quite a lot already. And Danny already shared with you that we do have some activities within our lecture session as well that invite you to check out things yourself, experience things firsthand. And what I would ask you to do now is to get a feeling for the first two quantum gates. And for that, we've prepared the following exercise. You can get to it by open this link, bit.ly/IQM-1, or scan the QR code on the right-hand side, and it will take you to an interactive circuit simulator. Once you're there, try applying the two mentioned gates, the H gate and the X gate. And please observe what happens to the qubit state. If you're quick, also apply the Hadamard gate twice in a row, while choosing 0 or 1 as the starting values. And you can change the starting values by clicking on specifically the numbers at the beginning of a row. Oh, the link is actually apparently not working, is it? Oh, no, it's working. I just mistyped it. So I'll also do that now, so you see what I'm doing. Here, that's the applet, and you can click here to change the input. You can drag and drop gates, and then you need to click the measure button, and you'll get out a measurement protocol here. I would reserve us 2 minutes to try us out for all of us, or 3 minutes. Failing to load. Let me just post the longer link as well. This is the longer link. That should really work though. Already see like first opinions in the chat what the two gates do. And I'm obviously not yet sharing what X and H are about. For us, that's now two operations that exist on a quantum computer. And I really want you to try it out first because before we debunk what they are about, what they actually do. Checking connection, someone is getting checking connection. I think that's the Cloudflare protection. I see opinions that the H gate is more like a randomizer. Have you tried to apply two Hadamard gates in a row as well, two H gates in a row as well? Have you tried that one and seen what it has changed or how it has impacted the result? Then I will kindly ask you to try that as well. So apparently if I look at your observations in the chat, the H gate functioned a little bit like a randomizer. Some people have written like 50-50. But if you apply the H gate twice, you'll always end up getting the output again. And actually, this means that for some reason, it can't be really like a randomizer, right? Because at least after that step, we wouldn't end up always with random results, independent of what we apply afterwards. And that's actually a very good first observation that the H gate, which rightfully, as you explained in the chat, is called the Hadamard gate, is creating what is called a superposition. It's kind of this state where it's to some part 0, to some part 1, or it's a linear combination of 0 and 1. And applying that operation again apparently reverts the operation. And this brings us back to the Bloch sphere visualization. The Bloch sphere visualization was this surface of the sphere. And we had 0 and 1 being north and south pole. The state we created after applying a Hadamard gate was the one that is pointing to the equator here. And measuring it would either determine it to go to north or south pole randomly with a 50% chance each. And I would ask you to use this tool now and try it out yourself. But before that, I would let Danny jump in for a quick question or a quick comment.
Yeah, so there's been a couple of questions in the previous simulator about what the 1, 2, and 3 represent. So you can think about that as time. So 1 is the first thing you do to the qubit, and then 2 is the second thing you do to the qubit, and 3 is the third thing. So you can think of that as moving along a musical notes, or moving along in time. So it's a sequence of operations that you do in a row.
Great input. Thank you, Danny. So now you have the chance to see what we've actually... Oh, thanks, Juha, for posting to the chat faster than we were. What we've actually just applied with the Bloch sphere visualization. And I'll also open that, but you can apply literally the same operations.
And just a quick reminder, we can't have people jump in with raised hands for questions, but if you put your question in the question and answer section, we can answer them there.
Okay, and if you try that stuff here, you'll potentially see that the Hadamard gate is indeed self-inverse, and it doesn't matter if you start from 0 or if you start from 1. It leads to the rotation being reversed. But what it shows us really is that this superposition state that we've created with the Hadamard gate is not a random state. It's a clearly defined state. So every point on the surface of this sphere is one potential state this qubit can be in. And it just happens that this one feels random 50-50. By the way, also there's this one or this one. But we can create states like this one here, where it points to like the northeast, maybe roughly where Germany would be, or something like this on the globe. And you could say, okay, this will actually lead much more likely to 0 if being measured than to a 1. You can try this out with one of the applets we have on IQM Academy later as well. But what I wanted to give you a feeling for really is that every point on the surface of the sphere is a state this qubit can be in. So it's not a third state which is called the superposition, but every point on the surface of the sphere is a potential state the qubit can be in. And obviously, it doesn't stop there. We also can express that mathematically, because I believe it really helps to see this not as being 0 or 1 at the same time, but to think about a qubit state as a linear combination of two states, being the two basis states, 0 and 1. We typically give every qubit a name, and this one is called psi, so Greek letter here, doesn't matter. And the notation we're using here is called the Dirac notation, and we would refer to this as a ket. So this is a ket, and a single qubit quantum state can be described mathematically as a linear combination between the state 0 and the state 1. A and B are so-called amplitudes. They are specific numbers, complex numbers, that tell us how much each of these basis states is present. And there is some condition to those. Because obviously you could say, well, they are just arbitrary numbers. But the thing is, there is still this law of measurement that when we measure, it's either one or the other. And obviously, we have seen a probability of 50-50 now with the state that we created, or a probability of 100 and 0. But there is not more than 100% probability for any of these outcomes. And this is what this condition tells us, that the squared absolute of these specific amplitudes additioned or added up needs to equal 1. So it's not like that the number itself tells us the probability, but they are related to the probability of measuring this specific outcome. And really, it shows again the thing that we've seen with the Bloch sphere visualization and that we've experienced with the applet firsthand, that superposition is not randomness. It's a precisely defined state. It's actually a precisely defined vector. So instead of this ket 0 and ket 1 way of noting the basis states, we could also note the basis states as vectors. One is 1, 0, and the other one is 0, 1. And then every single qubit quantum state can be described mathematically as a two-dimensional vector. And with that in mind, every operation that we apply can be expressed by a matrix. So we have changed the state by applying operations. If we now represent a state by a vector of dimension 2, an operation just becomes a matrix. For example, the X gate that we've just applied, that kind of functioned like a classical NOT gate but in quantum, can be written as a matrix as 0, 1, 1, 0. And if I apply that with a vector that has 1 in the first row and 0 in the second row, what I would do is I would multiply 0 by 1 plus 1 times 0. So I would end up with 0 in the first row, and I would multiply 1 by 1 plus 0 by 0, and a 1. So I end up with a 1 in the second row. And that's how you could mathematically compute the effect of an operation such as X. And the Hadamard gate also has a vector, a matrix representation. It would just look like this. So if we would multiply our basis vectors to this, like the vector for 0 and the vector for 1, we would end up getting these specific states. So one of these superposition states can be described as 1 over the square root of 2 times ket 0, or times the vector, plus 1 over square root 2 times ket 1. And the only difference here is if we apply Hadamard to the 1 state, we end up with a minus sign here. So it looks very similar in terms of magnitude of those specific parameters, but there is a minus sign. If we check back on this condition of how measurement is determined, because essentially how likely we measure the first outcome, ket 0, is determined by evaluating the absolute of A squared or the absolute of B squared. And that's the second result, obviously, if we want to measure, or like the likelihood of measuring 1. And if we apply that to both of these things, it doesn't matter if there is a minus sign in it. So that's why the probability was the same, independent of if we started to create the superposition with a Hadamard gate starting from 0, or if we started to create it from 1. And or if we started from 1. But it still makes a difference because they are two different states. They are at different positions on this Bloch sphere we've just visualized. And obviously the X and the H gate are not the only gates. There are other types, for example, other rotations around other axes of the Bloch sphere. There is a Z rotation that rotates around the north-south axis. There is a Y rotation that rotates around the Y axis. And obviously we can also split a rotation in half, in quarters, or whatever. You don't always need to rotate by 180 degrees. You could also rotate by 90 or 45 degrees. That's what you do with some other gates. They have separate names, and we'll see them, or you'll see them in your homework when you work with Qrisp on creating some specific quantum states. One of these gates I would encourage you to explore yourself now, though, which is the T gate. And you've already opened the Bloch visualization in the past, and we would need that one again. I'm curious to read from you. What do you see when you sandwich a T gate? Oops. I just figured I posted the wrong link in the chat, but I've also put the wrong link on the slide here. I can quickly fix that though. Here is the link. I mean, you can also do it in the Bloch sphere. That's fine. But it might also make sense to try it out with the applet I just linked. And if I do that and go down to where I see the T gate with the circuit editor, I could obviously sandwich this between two Hadamard gates. And you'll actually see that I can influence the chance of measuring a specific outcome. And you've seen I've changed here from measure, a single execution of the circuit, to like measuring 1,000 and showing the distribution. And that's something very typical when working with a quantum computer, because we are often confronted with probabilities. And doing just one measurement is pretty bad for statistics. That's why you typically do like 1,000 measurements, and then you look at the resulting distribution and derive your conclusions from there. But we can see that we can influence the probability of specific states. And on the small scale with 1 qubit, this is kind of a nice thing to play around with. But on the larger scale with algorithms that we want to solve, think about it that we can influence the probability or likelihood of measuring a specific outcome if we do the algorithm right. And this is what we always try to achieve when we do quantum computation. So the thing is, we've now worked with 1 qubit, and 1 qubit is still not very exciting. That's why we need to look into what happens if we add more qubits to the system. Because obviously 1 qubit alone isn't very useful. And just like 1 classical bit can't do much by itself, we need multiple qubits in order to get really powerful quantum computing. And if we consider now a system made of 2 qubits, we can write them like this, like the first qubit is in state 0 and the second qubit is in state 1, or typically this will be like written as this, ket 0, 1, which is this state where first qubit state 0, second qubit state 1. Sometimes also this tensor product is used to describe this mathematically. And we typically would say that a state such as this one, where the first one is a superposition and the second one is 0, this one can be decomposed into 2 individual qubits. So we can say qubit 1 is in this state, qubit 2 is in this state. We will refer to this as a tensor product state or a product state. So on the Bloch sphere, the left qubit kind of points on the equator to some direction, and the other one points to the North Pole. And we can also measure the qubits independently. The outcome of the first qubit will always be determined by this expression. The outcome of the second qubit will be determined by this expression. They are not correlated. And now we want to check something different. We want to explore a specific 2-qubit gate, which uses the so-called C0 gate, the C0 or CX gate. The gate operates as follows. It operates between 2 qubits, where 1 qubit is the control qubit. That's the one with the smaller bubble. And the other one is the target qubit. That's the one that is being controlled, that has the X here. And what it does is it flips the state of the target qubit if the control qubit is in state 1. So in case it's a 0 here, nothing happens. But in case it's a 1 here, it actually changes 0 to 1 and 1 to 0. So similarly to how the X gate behaved individually, it's just not applied in those cases. And the question I have to you now is, what happens if the control qubit is not like in 0 or 1, but it's in a superposition state of both 0 and 1. And you can check the following link that Danny is posting to the chat or has posted to the chat to figure out what it actually would mean. Oh, Nadia has posted, thank you. And clever people have guessed that we've just replaced the number from 1 to 0, from 1 to 2. And please write your experience to the chat. I see already a bunch of very good answers. I would give everyone the time to kind of experience it firsthand. So I think what you've experienced is that if the control qubit is in a superposition, the measurement result of the target qubit depends on which value the control qubit now assumes. So we will either see both qubits 0 or both qubits 1. We'll never see a mixture between if we do a circuit like this. And this is what we call entanglement. This combination of gates creates entanglement between two qubits. And if we would only measure the state of one of these qubits, we would already determine the state of the other qubit, because it would automatically be known. There is just two combinations of those, of those two qubits, 0, 0 and 1, 1. And only with entanglement is it possible to create truly arbitrary quantum states. And every two-qubit system can be mathematically described also by a linear combination. In this case, by a linear combination between 4 different basis states, 0, 0, 0, 1, 1, 0, and 1, 1. So the vector length would actually be 4 in case we would write it as a vector. There is also this side condition that the measurement needs to add up to 100%. And the state that we've just created, we can also write in this format. It would look like this. 1 over square root of 2 times ket 0, 0 plus 1 over the square root of 2 times ket 1, 1. And now the question is, okay, but what's now the state that qubit 1 is in, right? So what if I would just be curious to see the state of qubit 1? And that's what we want to check now. So the problem here is that there is no real way of saying, oh, this is now, qubit 1 is now in this state, qubit 2 is in this state. Because the individual qubits cannot be assigned their own well-defined state. And I can show you why. Let's state that let's say the state we generated was again this one. And let's really now assume, even though kind of it's not possible, that we can write it as a combination of two independent qubits. That would mean there is some combination of A, B, C, and D, so that the tensor product of this, so it's a product state, equals this entangled state that we just created. And firsthand, we might think, okay, this should somehow be possible. And I would do high school math and do the multiplication, so binomial formulas. And I would end up with AC times ket 0, 0 plus AD times ket 0, 1 plus BC times ket 1, 0 plus BD times ket 1, 1 equals this one. And now I do just comparison. AC apparently needs to match 1 over square root of 2. AD needs to be 0 because it doesn't appear on the left-hand side. BC needs to be 0 as well because it doesn't appear on the left-hand side. And BD needs to also match 1 over the square root of 2. What does this mean? AD equals 0 means either A is 0 or D is 0, or both. Let's assume A is 0, then that would mean that if I multiply A by C, I would end up having 1 over square root of 2 equals 0, which is obviously wrong. So this doesn't lead to a good conclusion. This leads me thinking, okay, A can't be 0, D needs to be 0. But then again, I have this formula. And if I put D here, I'd end with the same conflict. I would have a formula saying 1 over square root of 2 equals 0, which is obviously wrong. So this means if we have an entangled state, we can't speak of individual qubits anymore because we can't, well, we can speak of individual qubits, but we can't assign them their specific individual state. It's not a product state anymore. It's not a tensor product between two separate qubits state. And that's the key point. No choice of A, B, C, and D in my formula here can satisfy all those 4 equations at once. And that means we have a state that is truly entangled, and we can only consider the full system of qubits. We need to think about all the qubits as one system. We can't think about them as individual qubits with individual states anymore. And that's the formal definition of entanglement, a state that cannot be factored into individual qubit states. The system as a whole has a perfectly well-defined state, but the individual qubits, they no longer do. And I think that's a really exciting thing. 2-qubit gates are obviously needed so much as butter to pretzels, as classical logic also requires 2-qubit gates to be universally useful. And this is also true for quantum computing. And actually, we only need 2-qubit gates. We don't need gates that involve more than 2 qubits. We can express all bigger gate counts that include more qubits by using single and 2-qubit gates. This can be proven mathematically. It's not something that we want to do today, but it can be done. So the only other matrix we now need to think about is, like, how do those 2-qubit gates look like? And this, for example, is how the CNOT gate would look like. So this is the matrix representation of the CNOT gate. And you could do the math and multiply it with any of those dimension 4 vectors and see that it will still have the result. Similar to single qubit gates, there is not just one 2-qubit gate, there are multiple. There is the swap gate, but there are also others. For today, we'll just focus on using the CNOT gate. And as I said, any arbitrary unitary, like any arbitrary gate, can be decomposed in 1 and 2-qubit gates, because at least tomorrow we'll use gates that involve more than 2 qubits. They exist, like you can make multiple controls that are controlling the same target. They exist, they can be defined, but they are typically used or implemented using only 2-qubit gates. As the proof is highly technical, I'll not do it today, but there are books like Nielsen and Chuang that is anyway always a good recommendation, or Nakahara and Omi. Nakahara is a colleague of us, that that can be checked if you want to see the proof. And yeah. So the third activity I would invite you to do is open the circuit editor, and for some reason, also for me, this link doesn't work anymore. Apparently it's too old by now, but I can copy it for you and create a even bigger state. So here it is. And I would ask you to create now a state or a circuit that creates entanglement between not just 2 qubits, but how in this case, 5 qubits. And you can try that by implementing that specific circuit as it's given here on the slide. And if you've achieved it, please post to the chat the state that you've created. And there are people that are really quick. That's a superposition of well, slightly different than the one I created. You started out with qubit 1 in a different state, I think. In order to realize the control part in this visual representation, what you can do is the following. You drag and drop this point, and you drag and drop an X gate here. Then you select both of them and hit this C to create a combined or controlled operation. I'll do it once again. The dot, which is the identity, and the X gate, selecting both, hitting control operation, and it combines them. So at least I end up with this state equal superposition between all zeros and all ones. And this is called a GZ state after Greenberger, Horn, and Zeilinger. Maybe familiar from one of the recent Nobel laureate ceremonies. And it's a very well-known state that you test or use when you learn quantum computing, when you work with a quantum computer, and things like that. So to conclude, what we've done today is that we've seen qubits can not only be in those two states that bits can be in, so not only in 0 and 1, but also in a superposition of both of them. In this case, they have a certain probability of being measured as 0 or 1. However, a measurement destroys their superposition. We've also seen that there are multiple different, like indefinitely different states that are linear combinations of those two basis states that are all superposition states. We've also seen that quantum computers use quantum gates to manipulate the states of these qubits. We've seen that even though the measurement results of a qubit are random, the qubit is still always in a precisely defined state. Now we've seen that two qubits can be entangled with each other. If we then measure the state of one of the qubits, we automatically know the state of the other qubits, and we can't assign an individual state to any of those like participating qubits. We can only view them as one system. This was it for the lecture session of today. Next up, we want to get hands-on. And for this, I'd say we do like a 10-minute break and we see us again in 10 minutes here. I'll stay around. Danny and Nadia, one of you maybe also stays around, that we can answer still open questions and stuff like that. But obviously there is still room later for that. So see you in 10 minutes, folks. We're glad about the feedback you provide. Thank you. Thanks again for the feedback. We're glad that you liked it. We'll still have like 7 minutes until we start with the YouTube link will only be shared afterwards. We'll still have like 7 minutes left until we start with the hands-on session.
I see a question about not getting a link to open an account on the IQM platform. I will check into that and try to get back to you momentarily.
For those of you who just joined, we were slightly 5 minutes over the time, so we extended the break into this session until 11:37 my time, so like 5 minutes from now when we'll start. Already joined by Raphael, who later will also have an active role for today, which is great. And I can't wait to see what awesome stuff one can do with Qrisp.
Hmm.
No, we're not yet done, Akhil. We just wait for us to take a little break after I've slightly extended the lecture part over what I wanted to do. So I had to go a little bit into the lab session. Will also guide you to how to contribute to Qrisp or to the open source project. That will pop up when we speak with Rafael later. The certificate is given out based on attendance. We've shared the link already once. Maybe we can share it again. I don't know if Danny or Nadia have it at hand. Then you need to enter there your email address. You need to attend at least 2 days, and you need to work on 2 of the problem sets by running things on IQM Resonance. A superposition is a linear combination between multiple basis states. And entanglement are specific states of these that can't be written as product states. We unfortunately don't provide internships remotely. We do provide, or we do sometimes offer internships on our website, on our career website, which is iqm.teamtailor.com, I think, and can be also retrieved on our public website. In general, we do have positions open if you want to check those out. The problem sets are both on the IQM Quantum School Academy website and will be available as a QR code within this one here. So we are back at 11:38 my time. That means we go ahead and start with the lab, which is hands-on, which will introduce us to the tools we need in order to achieve great things with quantum computing. And we need to check out what do we need to cook really cool quantum programs. And we will use 2 ingredients for those. We'll use IQM Resonance, our IQM cloud platform, but we'll also use Qrisp, a super cool quantum computing framework that I'm a big fan of, but that also really is very approachable, very intuitive to use for newcomers, but also very helpful for seasoned developers, seasoned engineers who want to really make meaningful research with quantum computing. As there are 2 ingredients, I would go through those 2 ingredients one by one. And the first one I want to check out with you is IQM Resonance. In order to use a quantum computer, well, you first need access to one, right? And IQM Resonance is our cloud platform that allows running quantum programs on real hardware. You've already, most of you at least, signed up for the IQM Resonance platform. So we made sure that your accounts are running and these kind of things. And I would also want to give you a short tour of the tool itself. So once you're logged in, IQM Resonance greets you with its dashboard. The dashboard shows you an overview of when IQM devices are available, like Emerald is available throughout the week here for me. My latest jobs that I've been running, which I'm in the wrong organization. That's why I was wondering why those jobs were so old. Now it looks more up to date. If we go on to one of these quantum computers like IQM Emerald, which is our biggest device available, we can see the details of this device, current calibration information, more on that later. We see the URLs to access these devices. We can see a get started notebook or launch directly in Google Colab with this specific starter notebook. For this tutorial today, we have prepared more elaborate notebooks for you that actually guide you through some tasks and stuff. But if you want to get started with your own problem or your own thing, this is for sure the way to go. It also provides a visual overview of the device. The same is available for other devices such as IQM Garnet, which is a 20-qubit device that we've put up last or 2 years ago. And besides that, you find information about how to use IQM Resonance. And most importantly, you can retrieve your API token from here. That's something you'll need to have in order to access quantum computers. And you get to there by clicking on the View Account here, and then there is a section API token. It will only show you the token once. You can recreate one here, or if you have never created one, it will show Generate Your Token as a button. I have created mine and I don't want to change it for now, so I'll just leave it as it is. But make sure you create your token and you copy your token. In this lab, I will show you how to do it. Our recommendation is that you, after the lab, and that's why we've said you should reserve 4 hours a day, you can do or repeat all the things we've been showing in the lab exercise on your own pace. And you can also go beyond that by the exercises we suggest as homework. In addition to that, you'll need some way to run Python. Can be your local device, can be a Google Colab or some other service. And that's what we'll use today as well. So before we do that, there is a second ingredient that we need to look into, because we still need a way to express our quantum algorithms. We have resonance, yes, to run it, but there needs to be a way to express how specific operations are performed in a specific time span. And this is where Qrisp comes in. Qrisp is not only similar to Crispy chips, pretty nice, it also is a high-level programming framework for working with quantum computers. And it's Pythonic, so it can be installed using pip or whatever tool you like. It also has a Pythonic syntax. It's open source. It was created in Berlin at Fraunhofer Focus, and IQM is actively contributing to the development as well. The features that are included in Qrisp is that Qrisp has typed quantum variables, so it offers a way of structuring your code, avoiding technical depth by having those variables that have some other benefit features. It's allowing for modularity, so qubit allocation that is automatic, allows for like separate modules. That's pretty nice. It has built-in arithmetic functionality, a lot of built-in libraries also for solving or approaching specific problem classes. It's compatible with a lot of backends, with a lot of other circuit optimizers and these kind of things. It has a pretty capable simulator and also has full support of IQM hardware. To give you a feeling for why I think that Qrisp is a pretty nice thing to have is that it allows me to focus on my ideas. Obviously, this is a very arbitrary example of doing some multiplication with quantum floats or floating point numbers in different frameworks. And the Qrisp version is not only the shortest, it's also the easiest one to read. This is a placative example, but this translates to a lot of other problems. I personally feel that Qrisp allows me to focus on my ideas, to focus on the actual quantum computing concept, instead of getting lost in like boilerplate code. But that's only my understanding. And I think there is no better way of understanding what Qrisp can actually do for us by speaking with one of its creators. And that's why I'm happy that I'm joined by my friend, colleague, and the co-creator of Qrisp, Raphael Seidel. Raphael, great to have you.
Yeah, thank you, Stefan. Thank you for inviting me.
So the first question, well, first of all, maybe you can quickly introduce who you are and what you do at IQM.
Yeah, so I'm Raphael Seidel. I did my master's in theoretical physics at RWTH Aachen University in Germany. And yeah, I worked for quite some time at Fraunhofer Focus, where I also started developing Qrisp. And very recently, I got hired by IQM for precisely that reason. So as you see, there are already a lot of fans of Qrisp at IQM. And yeah, so now IQM will heavily support Qrisp by having me as the lead developer, but also a whole team of Qrisp developers. So yes, Qrisp is now a cross-organization quantum SDK.
Awesome. So we're now joined by a lot of students here who just learned the basics of quantum computing. How would you describe Qrisp in 1 or 2 sentences to them?
I think Qrisp allows you to enter quantum programming without having to learn all the technicalities that are required to program these devices. It allows you to become creative much faster than with other SDKs like Qiskit or Pennylane.
Cool. So you co-created Qrisp and you just mentioned other frameworks. I was wondering what was missing, frustrating about the existing approaches back when you started to work on quantum computing and on Qrisp that motivated you to build something new and different?
So when I first started getting into quantum programming, it was very frustrating because even when you wanted to do something super, super simple, you had to write dozens of lines of code. So that basically means you would need to remember all of this, or you constantly had to look up in the documentation, and that it just eats so much of your time. And me personally, I love automating things to make myself, but also others more efficient. And that was basically how the idea for Qrisp was born.
Was there a specific kind of problem or a specific challenge that you wanted to solve when you were thinking, okay, I need a better way to write this now?
Well, I remember one of the first quantum programming exercises that I did was implementing a simple addition. And in classical programming, that is something that is super trivial, right? Especially in Python, you just write the plus operator and then it adds you the numbers. But with programming tools like Qiskit, you easily spend hours on implementing something as simple as that. And even then, it is still just a prototypical demonstration. And that is something that motivated me that there really needs to be a change.
I see. Very interesting. From a developer's point of view, okay, you had this idea now. I need to start having my own tool that supports my thinking better and that enables me to be quicker on the things I want to solve. But I would imagine this was not easy. So creating a new project with new concepts from scratch is never easy, right? So from a developer's point of view, what was the hardest part about getting Qrisp off the ground?
Well, I'm going to answer with something technical. So the way that Qrisp operates is that it has this internal organization system of how it treats several quantum variables. And so when the quantum variables are created, they are located into their own tracing system. But when you entangle different quantum variables, these tracing systems, they kind of need to be merged such they are then in the same tracing system. And getting this kind of merging, but also the general orchestration of the whole thing to a level that the user really doesn't notice at all that there is something like this going on in the background, that was really challenging to get all of this nailed. But it now works, and yeah, I'm pretty sure you're not going to notice it. So yeah.
That's always the good thing. If someone else has solved the problem for me and I don't notice, that's, I think, the best thing that can happen to me. So kind of you were very technical in describing this. Did I understand correctly that kind of the challenge was in automating the resource allocation for the user?
Yes, the resource allocation, but also the general orchestration. How does everything work together? That is, I mean, as you can imagine, like with a programming language like Qrisp, there can be a lot of like different situations, a lot of user intentions, a lot of user stories that can appear, and like getting all of this under one head to function seamlessly. That was really the challenging part. But yeah, it's done now, I would say, and it works great.
Awesome. How would you describe? So obviously we have a lot of students here that or learners that are new to concepts like gates, circuits, and these kind of things, also superposition, entanglement. And we all were at this point ourselves at some point in time as well. I still remember all the physics vocabulary that I was bombarded with when I read the first book about quantum computing, when I needed to write some grant proposal and stuff like that. Where would you say are the biggest challenges when moving from understanding these concepts now to actually building quantum software? And maybe how can those be addressed by now using Qrisp, or how are they mitigated by Qrisp?
So I think as quantum software in the past was mostly individuals who program down their quantum circuits, and then they have some prototypical demonstrator who does what they wanted to, and that is basically the end of the life cycle of the quantum software. But if we're looking into the future, we also need to think about how quantum software will be built on a larger scale. And that in particular means collaborative quantum software development. And this is precisely where quantum programming tools that use quantum circuits as their programming interface will break down. Because you cannot really work collaboratively if you're just creating quantum circuits. Why is that? Quantum circuits themselves are like an incredibly primitive data structure. They're very general. You can do whatever you want. That's true. But it's also like really hard to actually write some documentation on what the quantum circuits do. Like you need to like figure out all the qubits, all the inputs, all the outputs. You cannot really write good documentation for this, and this is something that makes it really hard to share quantum software if it's written in terms of circuits. With Qrisp, this is different because in Qrisp you don't create quantum circuits, you create functions that operate on variables. And for that, we already know how to create documentation. As a matter of fact, there's a whole classical ecosystem that allows you to write proper documentation for functions and variables. And this is something that we lean heavily into Qrisp, and we're also already getting the fruits out of this.
Awesome. You also mentioned about that we get even more fruits out of this in the future in your explanations. Are there exciting new features or developments that users can expect from Qrisp within the next year, besides keeping the API from having breaking changes?
Yes, absolutely. So in the past years, yeah, it's been some time. We put together a really exciting implementation of Shor's algorithm that would, yeah, compile Shor's algorithm with a really minimal amount of code required. But like many other frameworks, it is written in Python, so it's suffered from some scalability issues. And this is not just a problem of Qrisp, it's basically the problem of any other Pythonic framework. If they have an implementation of Shor's algorithm, then it's usually rather slow. And that means that you can only compile Shor's algorithm for inputs with like 20, 30 bits, something like that. But in the past months, we fundamentally overhauled the Qrisp compilation pipeline. And with that, we're hoping to really scale up the whole thing. And yeah, I mean, I don't want to promise too much, but I think we have good chances of actually reaching 2K bits.
Nice. That sounds really exciting. So well, we've already spoken about the future, but let's get back to the present. If you could give the students one piece of advice as they now begin their journey into quantum software, what would it be?
Well, for that, I want to quote one of my favorite scientists, Richard Feynman. And he says, "What I cannot create, I don't understand." And what I want to tell you with this is that in order to really get into something, you need to write it down in code. If you're standing in front of an algorithm and you want to become an expert on it, the best way to become this expert is to actually get your fingers dirty and write the code to do this. And this is also how a large part of Qrisp and its algorithms came together. People just reading a paper thinking, wow, this is interesting. Just gonna write it down myself, even if someone already wrote it down. And eventually, we sometimes improve the algorithm. So quantum software engineering itself is still relatively new as a discipline. So there are actually some still low-hanging fruits. So I encourage you to get down and dirty and implement algorithms.
Speaking of getting down and dirty, I think people can also get dirty with a Qrisp. How can, if someone now is like motivated to contribute actively to the development of Qrisp, is there a way to participate? I heard it's an open source project. What would you recommend?
Yes, Qrisp is an open source project, and we are very much open for contributions. If you have any ideas, you can either write me or my collaborators an email. The email addresses are on the GitHub repository. You can also join our Slack server, or you can also just open a GitHub issue or a pull request. And this is how you can engage with us, and you can look at the other pull requests that are already there. We're very open to discuss your ideas with you.
Awesome. Well, thanks, Raphael, for joining us. We're now excited to try out Qrisp ourselves. You have now, you also have now a face of who is responsible, or one of the people responsible for the tool you're using. There are obviously more. One of the contributors, Niklas, is also in the chat active and helping out with links to Qrisp if you want to see where you can contribute. I would say we give Raphael a big round of applause, even though that's not really possible in Zoom. But if you find the emoji or react button, please feel free to do so. And I'm taking back full control now and would want to show you how we can actually get started of running things within Qrisp. Well, let's go ahead and look at my screen again. The notebook I'm using is the following one here. You can find it behind this QR code and can save a copy for you. This is a Google Colab link. You can obviously set up your own local Python environment. It has, like always, the typical, you need the right Python version and stuff. So you need to have Python 3.11. That's why I recommend working with Google Colab. The link will be also posted to the chat, as has been done now by Danny already. And I will show you what you need to do in order to work with that one. So this is how a Google Colab looks like once you've opened it. It's a so-called Jupyter Hub or Jupyter Notebook engine, and it allows us to mix and match between documentation and code. And that's why it's particularly useful for anything that you want to show, share, or demonstrate. It's not maybe the one you use to run your web service on, but it's very good if you want to have a mix between explanation and code. And one important thing to do, you normally go to the top right corner here and start your Python engine. I already did this, so we're quicker here. One important thing is to check that you have the right Python version. Currently, the stack is optimized for Python 3.11. That's why we recommend always to work with Python 3.11. Python 3.12 support is added. It will be deployed next week, but you can do that by going to the bottom right corner, select Change Runtime Type, and make sure you have 2025-07 selected here as the runtime version. And if you have that one running, then you just start with the first two cells. The first one is just updating pip, the package manager, so we don't have any surprises there. And the second one is installing the Qrisp package. I've already done this, so we're quicker. And what we do here now is we want to create code that creates different qubit states with Qrisp. And I'll walk you through what those code cells do. So here we do create single qubit variables, and we just want to create the four famous states we have been using and seeing now pretty often. State 0, state 1, state plus, state minus. And in Qrisp, everything is a quantum variable. So what I do is I create four different quantum variables, 0, 1, plus, and minus, and assign every one of those a single qubit. That's why there is a 1 here. And now, well, if I would execute that code cell, it would already give me some result. But the results are all the same. They're all 0. That's sad. But obviously, I've not applied any operations, right? How should those states be different just because I named them different? And that's what we do with operations within Qrisp. And obviously, there are a multitude of ways of doing this, and I'll just use the gates we've been using before. So in order to create a 0, I don't need to do anything. I already have it, right? It starts out being 0. But in order to create a 1 state, what I need to do is I need to apply an X operation onto this specific qubit. And I do that by applying the X gate to the quantum variable 1. If I now execute that and let it run, thing is, it feels slow for 1 qubit, but it gets very, very fast for multiple qubits. So the simulator is pretty good there. But you see, I end up with measuring 1 as the second result in 100% of the cases. This is how this needs to be read. The state plus and the state minus obviously are still not fully done. So how have I created plus state? Well, I've created it by applying a Hadamard operation, right? So similarly to X gate, there is the H gate as like a method or function called H. And if I now execute this, I see, oh, the measurement result really is 50% of the cases 0, 50% of the cases 1. What I also see is that I have the state vector here. That's typically something that's not visible to me when I run it on an actual quantum computer. This is just retrieved by doing the matrix operations that we've seen and discussed, and essentially doing the classical math to retrieve the state. And I can also now create the minus state, but I would actually leave the minus state to you as a homework, figuring out how I get to the minus state. I can say so far that you at least need 2 operations, most likely. There is another homework where we ask you to combine a multitude of different gates to create a more difficult quantum state. The state minus 0.5 plus 0.5 times I the complex number. You have code here that checks if you have really created the right state. This is a little bit more tricky and requires for sure some experimentation to figure it out. What I recommend is checking out the Bloch sphere to get help which operations might lead you to the right state. You can also write it as a vector and then think about which operations in matrices do I need to apply in order to get to those states. Next up, we obviously want to run what we've just been doing on IQM hardware. And for this, the next cell will prompt me to enter my API token. As I don't want to share my API token with all of you on screen, I've already executed that cell before, so you don't see my token. But what you will need to do is you will need to execute that cell, and then a little prompt window will appear where you paste your API token that you've retrieved from Resonance. So once you've logged in, this is the token you need. The next cell is already ready-made code that imports a specific class, which is the IQM backend class, specifies the API token as a parameter to that class, and the device instance. The device instance can also be retrieved on Resonance. It's the name of these devices. If you click on one of these devices, it's essentially the name here, Sirius, Garnet, or Emerald. That's the ID. In the first thing here, I'm using Sirius. Let's see how high is the load. Okay, Emerald I shouldn't use right now. The queue's pretty long, but Sirius looks pretty good. So I'm executing that cell now, and I'll see that wrong account. Oopsie. I need to log into my regular account. Oh, I was too slow, apparently. Yeah, but this is the job I just ran. 12:06, that's my local time. And what I'm seeing here is, okay, I see roughly the same distribution that I had before. I could also specify here, like, how often do I want to sample from this device? So if I hover over the get measurement, you see there are multiple parameters that I can use. I can use the plot option, then I would get a plot of it. I could use the shots option. So now I have maybe used, I think 1,000 shots is like the default, but I can also increase that number and say, I want to have it run on the quantum computer 10,000 times. Let's see, maybe I get a more equal distribution between the two results, because that's what the law of big numbers is going to tell me. As you can see, it's now already running here. Now it's completed. Took a little longer, obviously, than the other one. And as you can see, I get a more precise statistics. It's still biased towards one, but that's kind of the thing with true randomness. It's not always 50-50 if I sample individually from something that has 50% probability for either of the cases. Obviously, if I do it a lot of times, I will most likely get more closer to 50-50. But that's just the thing. There is randomness involved. Then the next thing we were doing this morning was we created entanglement, and we can do the very same thing that we do with the visual circuit editor in Qrisp. And what I do here is I define another quantum variable. This one is using 3 qubits, but I only need 2 here. And it applies a Hadamard gate now on the first of these qubits, and a controlled NOT operation between the first qubit here and the second qubit here. And in the end, I want to get the measurement results as well. So if I just execute that cell, and I've not specified a backend, so it will run in the simulator, I get the result that I was expecting. Right? The state that I created was 50% of cases 0, 0, and roughly 50% of cases 1, 1. Cool. I can also print the quantum circuit diagram that is underlying my code. If I do that, I would need to do print quantum variable, and it has this attribute of the quantum session called .qs. And if I print that, I see, okay, this is my quantum circuit. Looks very familiar, right? Actually, we already learned that a Bell state between 2 qubits is nice, but not nice enough. That's why the next task here is to increase it by using 1 additional qubit. So one thing I obviously have to make sure is that I'm also using 3 qubits here. And then what else do I need? So if I run that and also print me the quantum session or the circuit diagram, I have this one. Okay, I have now 3 qubits, yes, but why on earth is it not the state that I wanted? I wanted all 0 or all 1, but I got all 0 or 2 1s and 1 0. Not quite what I wanted. So what we've been doing is we added additional CX gates. I can do this in code as well, right? It's just a different way of expressing my idea. So what I do is I define a C0 gate between the quantum variable index 0 and the quantum variable index 2. And if I run that and then also print the according diagram, it looks like this. Cool, it looks correct. It looks slightly different though than the one I was doing in the lecture session this morning, right? So if I want to have the very same visual, I may do a control NOT operation between the second and the third qubit. But independent, if I do one or the other, it's still logically the same result that I'll measure. It's creating the same entangled state, even though it's creating it slightly differently. So this was now simulating a GZ state on my not on my notebook, but on this Google Colab. But I can also run this on actual hardware. And I can do this using the very same code I was using before. And I'm just checking the Q length just to be sure. So if I go here and execute that cell, that again does from Qrisp interface import IQM backend, quantum computer equals IQM backend, API token, device instance, and get measurements. I can define the shots, but I can also change the device instance here. I was using Sirius before, but actually now here I'm using Garnet, one of the other devices. They are different in the way they look. So this one has a central computational resonator, which the qubits are connected to, whereas the Garnet device has this nearest neighbor connectivity. But for me as a user, currently I'm not optimizing for either of those. I'm not really looking into how they are done. That's something you'll see on day 3. So I'll just execute this now on Garnet. I can go back again and watch my job being processed locally, sent to the server, and now I'm seeing I'm waiting here for my job being executed, but it's already done. It was a little too fast for me to even show you. And this is the result I just got back. And if I go back here, this is the result I've obtained. And that now looks interesting. It has more results than I expected, right? It has all 0s, it has all 1s, but there are other results. There is 1 1 0, there is 0 0 1, there is 1 0 0, there are a lot of other ones. And the reason why this is happening is because in the simulator everything's perfect, but we're speaking about the laws of the smallest particles of the universe, or smallest elements of the universe, quantum mechanics, and protecting those from external influences is very tricky. And that's why we see noise being introduced to our computation. And that's why we end up with some states or with some results that we have not really anticipated. But the good part is the 2 most likely results are still the 2 we expect. It's just that there are some others. And there are some questions in the chat about an error in the Colab. It's just, I think, because if you run the first cell that upgrades pip, that's quite normal that you need to restart the Colab environment. That's really part of the process. If you update or install packages, specific ones, then you need to restart the environment so that the Python environment can be reloaded. Just as a side note, but I have more time in the Q&A later to answer these. So that's what we see here. And I'd actually want to elaborate on this a little bit more, because we typically differentiate between different eras. And because I saw the question in the chat, indeed, all the materials are still locked, but you can download the individual notebook that we're using today under the day 1 section. The download all button will only be enabled after the school and will include also like the other materials we've been using. And that's why it's not yet shared. For today, you just would need to use the part that is under section day 1. So if I go into my browser on the Quantum School page and scroll down to day 1 here, you see that we have the course material linked here. Oops. Here on the course materials, you have the lab notebook. And download all really is then in the end with everything, kind of. So, going back to me explaining you what the quantum computing errors are about. So, we've seen that current day quantum computers, great devices, but they are still having erroneous operations, noisy operations. Every operation introduces some kind of additional error, slight error, small error maybe, 10 to the power of -3, but obviously they stack up. So every operation we add, the overall fidelity, as we would call it, of our algorithm decreases because the errors stack up. There are strategies to prevent those from happening, to reduce their impact, and so on and so forth. But that's something for a different school, so not something we can cover in this school, but there are tools that are provided in our stack. There are tools that we work on internally. There are tools available in literature on how to reduce these errors. But for now, our understanding just needs to be that quantum computing errors in the current age are still suspect to some errors of the operation, of the environment, of the measurement. And also, we have a moderate number of qubits with a limited connectivity. So not every qubit is connected with every qubit. And that's why it makes a difference on how you connect the qubits in your G8Z state. It doesn't make a difference if you just use 3 qubits, but it does make a difference if you use 15 or 20 qubits. Then you really end up thinking about, okay, can I maybe allow the computer to map this problem more perfectly towards a specific topology if I do this or that? And you can, in the homework, explore how you need to apply C0 operations to kind of match the topology of the hardware. And it's just one type of noise, those slightly imperfect gates, but it's the one that's the easiest to visualize. And that's why I wanted to show this to you first. And I do this by again switching to my browser and having here the Bloch sphere open. We've seen this before. It's just that now, if I apply that operation, it slightly over or undershoots. I forgot what actually, but you can see it's slightly not on South Pole again. And obviously, the more I apply this, the more I drift away from the results I have expected. It's just one example of what type of noise influence a quantum computer. There are multiple of these. But it's part of the challenge, and also things that people in our company, people in other companies are work on to constantly improve quantum computation. And it has multitude of causes. So quantum computers are very, very hard in a way to create, because obviously you want to protect those qubits very, very good from the environment. You don't want radiation, you don't want magnetic field changes, you don't want shaking, you don't want heat or movement. So we cool it down, we isolate it with metal enclosures, but still we need to be able to make computations with them. So we still need to be able to control them. And that's kind of the conflict we're in between constantly protecting it from the environment and still enabling those those operations that we use for computing. And those errors are typically named as NISQ, for noisy intermediate scale error. And the other error is the FTQC error, the fault tolerant quantum computing error, where we have all these errors corrected automatically for us. And error correction is based on redundancy, both classically and quantum. The thing is, while we can simply copy classical information, we can't easily copy quantum information, because we've heard and we've learned that any measurement destroys, for example, the superposition. And the fact that this is the case requires us to think differently about error correction. There are protocols on how to enable this, but still one single fault-tolerant qubit requires multiple physical qubits that are present on the chip. Also, noise needs to be reduced under a certain threshold, and this is what people are actively working on. It's a very exciting field to work in, I think. The goal, obviously, is to get from the top left of this diagram to the top right of this diagram, bottom left to the top right of this diagram. And things like connectivity of qubits, speed of operations, and other parameters can bring down these requirements of where this starts. So this is not a sharp edge. This is just now some way where this was put. So it really depends on a lot of aspects that need to be considered. But before that, there is the hope for some like NISQ utility era, where we can use the current day devices to have meaningful applications for specific industry verticals that allow us to solve some tasks better, faster, or using less energy than with traditional computing approaches. A lot of these are hybrid approaches. A lot of these are okay with some noise being present. And there is still enough room for people who want to explore and consider investigating how to get from where we are now to either NISQ utility or fault-tolerant quantum computing. So it's an exciting research field, and you can find a lot of cool research papers being published throughout the year that show cool, new, exciting approaches on how to do that. What we recommend you to be doing is, now that we've walked through the notebook once, that you go ahead and take a look yourself at this notebook. Go ahead and optimize the G8-SET circuit for this qubit topology of IQM Garnet with the connectivity in mind. I will not solve this for you, but what I want to show within Qrisp is some outlook, what more Qrisp can do. So you could say more crispy content. I just unfortunately don't have any chips with me. But Qrisp, as I said, has a lot of built-in functionality that allows us to do a lot of cool things. And besides the quantum variable, there are other types of quantum variables, like the quantum modulus. Modulus operations is like, I don't know the English word of Restklassenarithmetik, but like calculating in rings, I think is roughly what it translates to. And maybe Danny could help me out. He's for sure having taught that a lot of times, but doesn't matter. So you calculate modulus a specific number. And I can define here this value to be 2. That's the initialization of my quantum modulus. And I can now do the calculation within this element. So if I add up 2 with 2, I normally end up with 4. But modulo 3, I end up with something different. And that we'll see after a simulation. And what I end up with is 1 as a result. I can obviously change this and do arithmetic in the quantum modulus of 5. And if I then do it, the result is still 4. If I add yet another 1 or multiply this by 2, I again end up getting 1, right? So I can really do arithmetic in here as well. That's just like one of the things. But then there are also things like you can use arrays to create multiple quantum variables within one. Here it's just an array of quantum variables of 1 qubit. That's the most basic one to do. And this could also be used to create a G at Z state. But you could also put in quantum floats or quantum modulus within this array if you have more complex logic. And that's also why we thought to adopt Qrisp as one of the frameworks we heavily support, because quantum computers advance and quantum computers will move into an era where we get away from small test programs towards having large, fully fledged software applications. And we want to be sure that the tools are ready so we can make use of that. And that's one direction Qrisp is going into. There are obviously other cool things that Qrisp offers, and I really recommend to check out the official Qrisp homepage to learn more about Qrisp. But obviously the first thing for you now is to run this lab yourself, try it out. When you install the packages, like after this cell, I think after the pip upgrade, you will be for sure prompted to restart your runtime, and that's totally normal. That's just happening when the pip version is upgraded within Colab. We just do this just to be safe that all the packet, like that there are no conflicts or reasons we can't really figure out remotely, so we all have the same setup and the same things. We are still around to answer all of your questions. So Danny and Nadia, if you've spotted any questions in the Q&A, which we should still discuss in the bigger round, please let me know those questions. Otherwise, every one of you, thank you for attending. It was really great to be able to show you what quantum computing is about. I hope you're slightly more excited than before. I hope that we could spark some of the enthusiasm we have for the topic towards you.